So there are 5 regular classes left. 2 this week, 2 next week, and 1 the week after that. So my agenda is today we're going to do, as I said earlier, we're going to do 2 machine learning techniques over and beyond the ones that we've already done. We have learned, Bayes network learning and naive Bayes classifier, and we then went into general classification, general learning last class, and the trade-offs there. Today, I'm going to tell you about easy algorithms for learning decision trees, and also perceptrons, which is single-layer neural networks. And the interesting thing is then we can also compare when do naive Bayes networks work better, when do decision trees work better, when do perceptrons work better. Okay, so that sort of gives you an idea of the role of bias in efficient learning. Okay, so sometimes you need to know what sort of pattern is there in the problem before deciding which of these learning algorithms to use. So that's part of what we will try to understand. And then after today, I'm hoping to complete the discussion on learning, and then we will go to first order logic starting next class, or hopefully if I'm not completed today, then there may be a little bit left on learning next class, but then most of next class will be first order logic. Okay, and then we will, I think it will be probably about 3 classes, and then I'll decide what we can do in the 1 extra class as well. Okay, so that's where we are going towards. Are there any questions? I'm pretty sure you have complaints. I have complaints about the test, but we can exchange those complaints probably by email. So yes.
So was the test was 65 points or
75? If you add up the numbers, it's 75. Yeah, I just wrote 65 by mistake.
So I thought 10 was additional.
Oh, free? No. No. Well, I can do one free thing in the end, as against multiple times. It was just a summation mistake. Yes.
I had a quick question. I'm not sure if this was, maybe I'm just missing something, but in the email you said about the redoing the test and handing it in, you said you take the weighted average of the 2 exams. Is the weight going to be at this?
That was a secret. You all did it anyway. So basically the weight for this is 0. So I don't have to actually correct this. No, I don't know. I mean, normally in the past I've done like, higher for in class and lower for at home.
Okay.
But in general, I thought, if you did this, I'm happy because several of you just basically made in different places, they made the things, the thing that's obviously kind of interesting to me is the specific things I said people do on the test and you should not do. You remembered that I said something about it, so you did it. Right? So for example, one of the things is to not do this. Not A or B does not directly resolve with A or B to give you null. It doesn't. Right? And I said this. I actually had a slide, and I said, under the stress of the exam, you would like to get that little square somehow or other, and then you'll throw it in. And believe it or not, 3 or 4 or 5 of you did that. But so it's hopefully when you did it at home, you probably looked at it more carefully. Okay. So it's not very clear how much of it was because of the exam stress, how much of it is because actually it did not get through. So this will give me an idea. Any other questions? Okay. Yeah, as I said, actually the interesting part of grading is, as I think I may have mentioned this, I think the Tolstoy's, is it Anna Karenina or something, which starts apparently by saying all happy families are alike. And every sad family every unhappy family is unhappy in its own distinct way. And so all completely correct exams are alike. There's only one answer for each of them. But different ways people make mistakes, you know, and they're very specific. In some sense, actually, this is why I think eventually, you know, you need the way the whole direction that of have a test that's computerized and you do it any number of times until you get it right. Okay, is probably the way to go. You know, I mean, I think the university system that you and I are in essentially, you know, goes its way partly also because of the human effort involved. You know, every time I ask you to redo the test, I actually have to grade it. You have to do it, and so you're unhappy. I have to grade it too. But eventually, getting it is way better than not getting it, right? I mean, getting the idea, even if in fact, I think I had a colleague once who told me that she always understood the entire material 3 weeks after the final exam. And, you know, from the point of view of grand scale of things, she's way ahead of the humanity, right? Most people live their whole life not getting it, right? So getting it 3 weeks later is fine, as far as I'm concerned. Unfortunately, it doesn't affect your grade, you know, in a positive way. But still getting it is useful, and so that's part of the reason to do it until, you know, multiple times until you get it. I mean, of course, you need the time, and you need to be able to spend the time, because each of you make the mistakes in this, you know, in a different way. I mean, I can only it's sort of, in fact, it's interesting to explain for each of you why, you know, understand why you made that mistake and try to figure out, you know. But then if I try to do this for the entire class, the rest of you who didn't make that mistake are bored to death. As I said, there are a million ways of making mistakes, only one way of doing it right, maybe a few ways of doing it right. Okay. Anyway, any other questions? Okay. So we are going to, as I said, look at this, how to learn this kind of logical formulas from data, okay? And so we have actually, to make our life simple, we'll actually use the same exact picture, essentially. We'll use the Russell eating habits, so that you have the same, you know, common basis for all of them. Except earlier we learned a naive-Bayes network. Now I want to learn a sort of a decision tree which asks a bunch of questions, and based on the answers to that question, you get to the leaf node. The leaf node says yes or no. And if it says yes, that means, you know, Russell will wait. If it says no, Russell won't wait. Okay. So obviously, suppose it turned out that, so the question of course is, what decision tree would you learn? You want to learn the decision tree that classifies the examples correct. Now, many a time, there may be more than one decision tree that classifies the example correct. Then you probably want to learn the simpler decision tree that classifies the examples correct. So, for example, in this case, instead of yes, 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 and no, 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 suppose all of these were yes. That means all training examples were yes. Okay, so Russell is really hungry. He doesn't mind. He'll just wait always for the table. Okay. Now I can draw, you know, a large decision tree, all of whose leaf nodes are yes. Or I can draw a very small decision tree, which only has one node, says yes. And both classify the data correctly, classify the training data correctly. Obviously, you think the one node is better than the longer one. Okay, why try to look for complicated patterns when there is a simple pattern staring at you? Okay, so presumably, so what we'll be doing is, it's easy enough. I hope you understand that if I were to give you a decision tree, okay, if I were to give you a specific decision tree, you can check whether or not, I mean, how many examples here is that decision tree correctly classifying, and how many is it incorrectly classifying? Do you understand what I'm saying? Suppose I give you a very simple decision tree which says it's only one layer, and it says raining, no, yes, that's it. That's my decision tree. Is it raining? And if it is yes, and if it's no, if it is yes, yes. It's no, no. That's my decision tree. That's a hypothesis about this data. Okay, now if I were to look at this decision tree, I can see whether or not this particular example is correctly classified by that decision tree. In this example, rating is no. Okay, if it is no, decision tree will say no. But the example is saying yes. So this is incorrect. It's an error. It's also a particular kind of an error, right? This is what? It's a false positive. Instead of it being a negative, it's a false negative. In the sense, in reality, it is a positive, but your learned pattern is saying it is a negative. Do you see what I'm saying? So if I were to make a decision tree, just make one up, I can check how good is it with respect to the data. Okay, and if I have some way of making decision trees, so if I don't mind, if all I care about is just find a decision tree that correctly classifies all the training data, then I just basically keep generating decision trees until I find one that classifies the training data correctly. But as I also pointed out, there may be many decision trees that classify the training data correctly, in which case you want to look for the one which has the smallest size in some sense. Okay? The smallest size can be counted in terms of the size of the tree, essentially the number of questions you are asking, the total number of questions you are asking. I mean, if you have two trees, you can compare them in terms of the size, in terms of the depth, in terms of the width, but one idea is just compare them in terms of the size, in the number of nodes, internal nodes. Okay? In that case, then essentially, you might want to go through decision trees in the increasing length, increasing size, in terms of decision trees with only one question, decision trees with 2 questions at most, decision trees with 3 questions at most, decision trees with 15 questions at most, and so on. And then the first time you find a decision tree that correctly classifies the data, you stop. That's a way of learning. It removes all magic out of it because it's just like brute force. You're just going through, you're making one hypothesis, checking if it works with the data. Making another hypothesis, check if it works with the data, and so on. Now, if I am doing that idea, how much time will I spend in trying to look for the decision trees? The one that is, the smallest decision tree that is consistent with the data. In the worst case, you will have to go through all decision trees. Now, the question then will be, how many decision trees are there? How many decision trees are there? Basically, we can see that decision tree is a representation for any logical formula. So, in particular, actually, if I were to give you a Boolean function, what would a Boolean function look like? It will say basically attribute 1, attribute 2, and then class. Right? And so, for true, false, true, true, false, and then you need to, class would be the true or false. Right? Okay. So a Boolean function would be given by basically giving for each of these possibilities, whether it is true or false. Okay. Notice that you didn't give all possibilities in the training data. The jump you are making is the training data is probably much smaller than the total number of examples, the total number of entries that will be there in the Boolean function, right? If there are n Boolean attributes, there will be 2 power n rows here, right? Okay, but you may not have 2 power n examples. There are a few examples here. Okay, so anyway, the question, of course, is then each of these rows. In the worst case, I can say each of these rows, I can make a direct single branch in the decision tree correspond to that row. Okay, and so that's like a way of arguing that every function here can be encoded as a decision tree. That means at least there are as many functions, as many decision trees as there are Boolean functions. There are 2 power n Boolean functions, which means the loop that you are going through will take you a long time to complete. Okay, so the usual thing we do in those kinds of cases is do a greedy method, for example. Because it just takes too long to find the optimal decision tree, you find a greedy you find basically a greedy method where you locally pick what's the best first question to ask. And then having asked that question, what is the best second question to ask? Having asked that question, what's the best third question to ask, and so on. If you do that, you are not guaranteed to get the smallest decision tree, but you are likely to get much better than the worst decision tree possible. Okay, so the so-called decision tree learning algorithms essentially pick the decision tree greedily, rather than run through the entire set of Boolean functions, entire set of decision trees. They construct one decision tree greedily. Okay, that's not guaranteed to be the optimal one, because in fact, if it is the optimal decision tree, then somehow you are able to do, basically, if it is the optimal decision tree, then you have to, in the worst case, go through 2 power n functions to make sure. Okay, the other interesting question is, how many examples do you need to learn the decision tree correctly, even if you are interested in doing it optimally? And that's what we were talking about last class, which basically told you that the number of examples you need, the minimum number of examples you need, is proportional to log of the number of hypotheses. Since the number of hypotheses is the number of Boolean functions, there are 2 power n. A log of 2 power n is 2 power n. So in the worst case, to learn optimal decision tree, you would need exponential number of examples. That is actually can be seen as a feature or a bug. It's a feature in the sense actually decision trees are able to capture every possible Boolean function. And there are 2 power n Boolean functions. That's why to differentiate between different decision trees, you will need exponential number of examples. Okay? Whereas if you are actually somehow looking for conjunctive descriptions, I'm not going to do decision trees. I'm going to assume that my data, the function here is not going to be a decision tree. It's just going to be one single branch of the decision tree. That means it is actually a series of questions at the end of which you will say yes or no. So I will say, for example, it would have to be a conjunctive function. If P is true, if P, Q, R are true, and S and T are false, then it's yes, otherwise no. That would be a conjunctive function. There is no disjunctions in the function anymore. And the number of conjunctive functions are only 3 power n, because in deciding the conjunctive function, you get to decide for each attribute whether it is present positively, negatively, or not at all. So 3 power n possibilities. And if you're only learning a conjunctive function, you don't need as many examples. You need only log of 3 power n, which is basically polynomial. Do you understand what I'm saying? Now, when I give you the data, do you know whether you're supposed to be learning, whether it's supposed to assume that it can have any Boolean function, or maybe it'll only have conjunctive Boolean functions? Unless I tell you, you won't know for sure. So if you want to be conservative, you have to assume it can have Boolean functions. And if it have normal Boolean functions, then decision trees are better than conjunctive functions. But on the other hand, conjunctive functions are easier to learn. It's the same thing again. If I don't tell you where I lost the keys, should you be looking for the keys under the light? No. But on the other hand, I didn't tell you where I lost the keys. You want to make your life easy, look under the tree, under the light, as against look in a dark corner. Okay, this comes up multiple times. You look for straight lines separating positives from negatives because it's easier to find straight lines separating positive negatives. Okay, you look for naive Bayes classifiers rather than fully complete Bayes networks because this is much easier to learn. And then similarly, oftentimes either though you might be learning conjunctive functions, looking for conjunctive functions rather than decision trees in the data. Right now, I'll tell you how to learn decision tree using greedy methods. Okay. Now, as I said, so basic idea is generate this decision tree piece by piece. Start from the top, ask what's the first question to ask. Okay? And then, so pick an attribute, split the examples that you have based on the values of that attribute. So notice that in the beginning, before you ask a question, this is sort of a recursive procedure. And imagine this is a Boolean classification problem. Okay? So there are n plus positive examples, n minus negative examples. So n plus plus n minus equal to n. That's the total number of examples you have. Okay? In the beginning, some n plus and some n minus such that the total is n. Now I've decided to pick some particular attribute, let's say A15. Okay? In the simplest case, it's a Boolean attribute. Okay? So A15 true, A15 false. What I'm doing is I'm splitting these examples into the set of these n examples where have A15 true, come this side. Set of n examples where A15 is false, come this side. Do you see what I'm saying? So then this would be, I would say, n15 plus n15 minus n not 15 plus n not 15 minus. Do you get what I'm saying? Okay, these are all the examples where the 15th attributes are, all these examples are ones where 15th attribute is true. All these examples are ones where 15th attribute is false. Of these examples, these many are actually belonging to the positive class. These many belong to the negative class. And then of these many belong to the positive, these many belong to the negative. You notice that examples can get lost when you're splitting them. So obviously, if you add all these four numbers, that will be again n. Okay? So my question then is, in the beginning, basically I have n plus positives and minus negatives, and I could have picked A15 to split, let's say, or I could have picked A17 to split. Okay? Let's again assume this is also, Boolean, although actually the way we'll discuss this algorithm, it doesn't have to be Boolean attributes. It can be multi-valued attributes. Okay, but we'll look at Boolean right now. So in this case, this would be n17 plus n17 minus n not 17 plus n not 17 minus. Okay, now my question is, I can either ask this question or this question. Which one should I ask? So if splitting on an attribute means you're asking the guy who has the data, okay, is A15 true or false? For that, for the example you have in your hand. And here you're asking, is A17 true or false? Decision trees are 20 questions game, the game of 20 questions. Okay? Of course, it's normally more than or less than 20 questions. Okay? So that's basically your issue. And so you somehow need to compare whether to ask this question or this question. Okay? Do people get this? Okay, now let's put some numbers here. Suppose, originally, this is 20, this is 0. What question should I ask? Don't ask anything. Right? I mean, I gave you true-false examples as the training data where all the examples had answer to be true. So you assume to the extent the training data is representative of the test data, then obviously all my questions also will have true. Actually, I tend to have a bias. I don't know whether you noticed or not. I cannot say a true statement. Everything, in a true-false statement is false for a completely crazy reason. Okay, so that's the bias you can learn. So if I ask true-false, there's a higher chance that probably what I'm saying is false. But you still have to figure out why it is false. That's where you have trouble. Okay, but in general, if I know for sure with certainty that it's all going to be false, then you don't need to learn anything. Just put false, 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 false. Okay, so if it is 20 and 0, you won't even ask any questions. Right? Okay. Now, suppose it's not 20 and 0, but it is like 10 and 10, which is pretty bad. Right? 10 positives, 10 negatives. And suppose if I split it this way, I get 5, 0, 15, 0. And then here I get 5, no, is that correct? Yeah, that's correct. Okay. Here I get 5, 5, 5, 5. Which question would you ask?
50.
What?
50.
This one, right? Because this basically, by asking this question, you know the answer. Whereas this question, after asking this, you are no better off than before. That's the intuition. That's how you figure out what question to ask. You ask that question which decides the fate of this example. It doesn't have to be positive or negative. All you need to know is, after this question, will I know for sure what's the fate of this example? If so, that's what I would ask. Agreed? Okay, so clearly in this case, there is no contest. This guy is no better than before. This guy is way better than before. After this question, you are done. So you will pick this. Now, what if I have 5, 1, 1, 14 here? Okay, and here, instead of 5, 5, 5, 5, it's 4, 6, 6, 4. Now I'm messing around. You know, I first showed you one real loser and one real winner. You can easily see the real winner is better than real loser. But in a normal example, you won't get real losers and real winners. You will get shades of losers and winners. And you need to determine that this guy is slightly less of a loser than this other guy, so we'll pick this question. You understand? Okay? So you can still see, remember the way we made this example, you can still see that this guy is still more of a winner. Because in some sense, if you are in this, then you are, essentially it's still able to, if the A15 is true, then there is a 5/6 probability that the answer is yes. And only 1/6 probability that answer is no. And if A15 is false, there is 1/15 probability that the answer is yes, and 14/15 probability that the answer is no. Right? So you would have really liked 1 and 0 here and 0 and 1 here, but this is pretty good still. The worst, of course, this guy on the other hand, if you look at this side, you have 4 by 10, 6 by 10, and 6 by 10, 4 by 10 probabilities. Right? Okay, so you still don't like this guy compared to this guy, because this guy is giving you a better chance of picking the answer, whereas this guy still is not, is nowhere near sure as to what the answer is after asking that question. Okay, the real worst would be one half, 1 half, 1 half, 1 half. That means you didn't tell me anything that I didn't know after asking the question. It's a completely irrelevant question as far as this problem is concerned. Okay, but this is not much better than this. And similarly, 1, 0, 0, 1 are the best answers. Right? Okay, but on the other hand, this is not, it's only a little worse than this. And so as you become worse and worse this side, better and slightly better and better this side, somewhere they become close enough. And so you need like some numeric formula to determine whether one side is better than the other side, not just your intuition. So I need some simple, expression which works on these trees. When I split an attribute, I split the examples using an attribute, it will tell me which attribute is what splitting. And then, just a second. And if I know, then if I have only 10 attributes, then I do this for 10 attributes. And then get that expression for each of those 10 attributes. And whichever has the best, I'll pick that. That's what is being greedy. Yes?
In the decision tree, first decision tree, the number of negative is 50, but the number of negative above is 10.
Which one?
In the first decision tree.
This one, yeah.
Number of negative is 15.
Oh, okay. Yeah, you're right. I mean, those numbers should make sense. So by now, actually, in fact, when I came here, you don't even have to remember this. Right? Actually. In fact, this is true. Okay? So the what you really want to, in fact, I mean, even though I actually messed up there in the sense that this couldn't have made sense in a real example, but ultimately what matters is what is the right question to ask, not where you came from, but after the question, how much work would be left after the question. After the question here, there is much less work left than here. Okay? Knowing this only tells you there was a certain amount of work that you had to do. After asking this question, there is less amount of work. And the question you ask is the one that leads to the maximum reduction in the work to be done. The one that leads to the maximum reduction in the work to be done is also the one after which there is the least amount of work left to do. Right? So that's why in relation trees, basically you can say, you can talk about the gain from here to here, or you can say just from each of these by asking this, what is the information content. That's the word we're going to use essentially. Now, to make sense of this, we have noticed that I'm using probabilities, right? And the probabilities basically are, I have event systems where these are all Boolean events, and each of these are Boolean events. So I have P1, P2. So they have two events, E1 and E2, such that E1 occurs with probability P1, E2 occurs with probability P2. Then the question is, what I would like to know is I want an expression which somehow becomes high when P1 and P2 are half and half. And becomes low when it is 1 and 0 or 0 and 1. Right? Half and half means you didn't learn anything. As it becomes more and more skewed towards one direction, you are learning more and more. This is captured by the notion of entropy. Okay? So we go the next. So basically all we are saying here is you want to pick an attribute, you split the examples in terms of that attribute. Okay? After splitting on the examples, figure out, let's assume, suppose you already decided which attribute to pick. Then you will have to split, suppose you decided to use this, then you have to split the examples in terms of this attribute. Here are all the positive, here are all the ones where this attribute is true, here are the ones where the attribute is false, and then you split them into positive examples, negative examples, positive examples, negative examples. Now, if in any of these branches, you only have positives and no negatives, or only have negatives and no positives, then you stop and say the answer is yes, the answer is no. That's it. You don't need to do any further. If not, then you recursively call yourself on that part. It's like a smaller learning problem now. Just like before. Remember in the top two, when I said if it was 20 here, 0 here, you said I don't need to do anything. Okay? It's only because it's like 10, 10, 15, 5, I need to do something because I still am not sure of the label of the data. So when having split, I will again ask myself, do I need to further split or not? I will need to further split if in fact the probabilities are not 0 and 1 or 1, 0. In which case, how do I split? I just recursively call myself. Whatever little program I wrote to pick the attribute at this level, I'll call to pick the attribute at this level. Except since I've already asked one question, unless you think people will keep changing their mind if you ask the same question multiple times, you don't ask that question anymore. You ask one of the remaining and minus 1 attributes. Okay? So that's a basic idea of this algorithm. Okay? It's going to recursively split. Now the only question is, how do you pick the attribute? And this example sort of gave you the intuitions behind how to pick the attribute. You pick the attribute that sort of pushes the probabilities to close to 1, 0 or 0, 1 in the Boolean case. Or even in the non-Boolean case, you want sharply peaked probability distribution. Okay? And you don't want to pick the, attributes which will basically leave the probability distribution as close to uniform as possible. Because the uniform distribution is the most amount of disorder. Right? Before you took this course, if you didn't know anything about this course, if you asked yourself, what is the likelihood of me getting a particular grade? It's, if there are 7 possible grades, then the likelihood of you getting the particular grade is 1/7. If you don't know anything more about your background, my background, this course, nothing. From after that, the rest of the time you've been trying to reduce that uncertainty, one way or other. If you're sunk, at least know that you're sunk, in which case at least you won't waste time on this course. If you're not sunk, push it towards a particular grade so that at least you know what it is. Right? Okay? So you're reducing the entropy. Reducing the entropy means increasing the order. In a probability distribution scenario, if you have a uniform distribution, that is the highest entropy. A pk distribution has low entropy. And even more pk distribution has even lower entropy. Right? Okay? That's basically what you want to capture using some expression, and an expression that you can use for that. Let's say, okay, so by example, this is basically saying what I said there, that if you were trying to split the original examples, you could split using patterns or type. If you split using patterns, you got patterns none, these are the examples. No positives, only negatives. Patterns sum, these are the examples. No negatives, only positives. Patterns full, these are the examples, 2 positives and 4 negatives. And if I split on type, then I get 1, 1, 1, 1, 2, 2, 2, 2. Which would you pick? Which would you rather pick? If these are the 2 questions you can ask, one of these questions you have to ask. Which would you rather ask? The patterns, because this one you're almost done here, and only this you have to work on. Whereas here you're not done here, you're not done here, you're not done here, you're not done here. Right? This is the intuition, and how do I capture it? And I want to capture it using entropy. And the way you define, and so of course now if you were to pick patterns, then I already know the answer here. It's yes. I already know the answer here. It's no. And now I recursively call myself on this part. And then maybe I ask hungry now on just this part. And the hungry gets plus minus and minus plus. So here the answer is no, and here I still need to do 1. Just one simple recursive algorithm. It's greedy because you never backtrack. You never ask, maybe I should have not asked patterns first. You just do the locally the best thing at every point. Okay. Now, as far as so basically I need to compute the entropy expression for this as well as this, and the entropy expression essentially is, okay, let me just write this here. For an event system, for an event system with E1, etc., En, that means there are n different events and they are mutually exclusive. That means if E1 occurs, E2 doesn't occur. E1 occurs, then nothing else occurs. E2 occurs, nothing else occurs. En occurs, nothing else occurs. And they are mutually exclusive and exhaustive. One of them will always occur. Exactly one of them will always occur, basically. And if I tell you that this has a probability P1, this has a probability P2, this has a probability Pn, then I want to talk about the entropy of this event system as this. It's a sum of, negative sum of Pi log Pi. Okay, now let's make sure that it makes sense. Okay, there are all sorts of ways of saying why this is a reasonable expression. But the simplest is to make sure that it actually works with your intuition. Okay, if I have a binary event system, and if I have P1 and P2, if P1 is 1 and P2 is 0, and P1, P2 such that P1 is half, P2 is half. Okay, if it is 1 and 0, you can see this is minus 1 log 1 minus 0 log 0 equal to 0. Or minus half log half minus half log half, and we again assume log to the base 2. Okay, that log of half is minus 1. Okay, so this is plus half, which is equal to 1. This entropy is 1, this entropy is 0. In fact, the entropy of any of these event systems at most will be 1. That means they are, at that case, they are the most disordered. And it will be at least 0. I mean, at the lowest, it will be 0. That means they are the most ordered in that case. Okay, so for a binary event system, if you draw this with respect to, remember in a binary event system, if I fix P1, then P2 is determined, right? 1 minus P1 is P2. Okay, so if I go P1 from 0 all the way to 1, and I draw the entropy on the y-axis, right? Clearly it will be 0 here, it will be 0 here, it will be high here, it will be 1 here. Unfortunately, it's not going to be one of these phase transition pictures. It sort of looks nicely like that. That's how it looks. Which is why you shouldn't be surprised. By the way, the answer for that is you are not supposed to be surprised that there are hard problems in the middle. If you are surprised at that, that means you are easily surprised. I actually said this. Go back to the lecture, and I specifically said you shouldn't be surprised at that fact. You should only be surprised that there is a narrow band where they are existing. I mean, there's a hard problems here, hard problems here. There's, easy here, easy here. There should be hard problems somewhere. They should be in the middle. You shouldn't be surprised at that. Okay. Similarly, here this is 1, this is 0. And obviously, not surprisingly, it sort of looks like some smooth curve, and it's a smooth curve. That's what the entropy looks like for that event system. But this expression is general enough that I can do it for any particular set of events. It doesn't have to be a boolean event system. It doesn't have to be a binary event system. Okay? So this is what I'm going to use to decide, which feature to split on. I want to split on the feature that leaves the entropy of the system at the lowest possible level. And if the entropy is 0, that means you're done. Okay, and if there are two systems, questions you can ask, this one will get you to 0.01, and this one will get you to 0.2, then you go with this, because this will get you to 0.01. That's arithmetic. So I converted my intuition into an arithmetic test. That's all you do here. Okay? The only question now, if I go back to my picture here, this is why I did not remove this picture until now, right? So here, remember, this is 5 by 6. If, for my example, I had a 5 by 6, 1 by 6 here. Okay? Then I'll write that I 5 by 6, 1 by 6 basically means minus 5 by 6 log 5 by 6 minus 1 by 6 log 1 by 6. That's my notation. I is basically my entropy. You can call it E if you want. Okay. So clearly here on this branch the entropy is I 5 by 6, 1 by 6. On this branch the entropy is I 1 by 15, 14 by 15. Right? By the way, you realize that I P1 1 minus P1 is the same as I 1 minus P1 P1. Right? Because the entropy is symmetric for Boolean systems. Okay, so anyway, I have this as the entropy for this branch, this as the entropy for this branch. What is the total entropy if I were to ask this question? that depends on what's the probability that after this question I will be in this branch or this branch. Right? Okay, I would be in this branch in this branch there are 6 guys total. And this is where I need to know how many total examples were there. There are 20 total examples, so 6 of the 20 will fall here. And 14, right, of the 20 will fall this side. So with probability 620, I will deal with an entropy of I 5 by 6, 1 by 6. With probability 14 by 20, I will deal with an entropy of 1 over 15, 14 over 15. So the expected entropy is 6 by 20 times this plus 14 by 20 times this. A nice real number. That's all I ever wanted. Because I can compare real numbers and say this guy is bigger than this guy. That's all. Right? Any questions on this? That's all I'm doing. Okay? So I'm going to run through this here basically. In the same thing I did here, I'm doing it for a more general case. So I originally had n plus positive examples and n minus negative examples. So the probability that an arbitrary example will be positive is n plus by n plus plus n minus. And probability that an arbitrary example will be negative would be n minus by n plus plus n minus. So my original event system is n plus n minus, whose entropy is this. If it was 0, I would stop. There is no point in asking any more questions. If it is not 0, then I have to decide to split. Suppose I was if I was going to split on feature fk, and it is some it has some j different values. Let's say in this case it has just showed exactly 3 values. No, it has actually in this particular case the way I wrote it, it has k different values. This feature has k different values. Okay. In this branch, fk has its first value. In this branch, fk has its second value, and finally in this branch, fk has its kth value. For the example. And then this is n1 plus, n1 minus, n2 plus, n2 minus, nk plus, nk minus. That's exactly what I'm doing here. In this case, it was just a k equal to 2, 1 and 2. Okay. So then the information contained for the entropy for this would be I of P1 plus P1 minus, and P2 plus P2 minus, Pk plus Pk minus, where P1 plus is N1 plus by N1 plus N1 minus. Just the obvious probabilities. Okay, and similarly this would be N2 plus by N2 plus N2 minus, so on. Okay, now I need to combine this, and to combine this I need to realize that the branch here I will get here with the probability n1 plus n1 minus divided by n plus n minus. The total number of examples are n plus n minus, of which n1 plus n1 minus of them have this value for this entry. Okay? Right? So then I'll multiply this by ni plus, so each ith entry, for the ith entry, this is the entropy, and I multiply that entropy by the probability of falling into that branch, which is ni plus ni minus by n plus n minus. Okay? And that would give me the expected entropy after asking this question. So now I can either talk about this was the original entropy, this is the entropy after. So you can talk about what is the gain. Information gain is entropy reduction. You gain information when you reduce the disorder. Okay? So you can either look for the attribute that has the biggest difference here, or you can pick the equivalently, you can pick the attribute which has the least amount of work left. That means the smallest value left here. If it is close to 0, then you are done. And they're equivalent, basically. So normally we just look at this and pick the one that has the lowest expected entropy left. That's it. So now you have the picture of decision tree learning. So you have a little recursive algorithm. You can write a little program for this extremely easily, right? And then it essentially just runs through the examples, classifying them, separating them in terms of what values they take for a particular variable into different bins. And then from those bins, you can compute all these probabilities, and from that, you can compute the expected entropy. This is decision tree learning. And it's doing it greedily because you're not going back ever on the question it asked. Okay? Now, the interesting thing, of course, is greedy doesn't necessarily have to be optimal. And the reason decision tree algorithms are not optimal, actually, in the example, in a homework example I'll make you do, it's about a party scenario in Seinfeld-Neuman. If they both go to the party, it would be a bad party. If any one of them go, it's fine. And it turns out it's sort of an XOR kind of a scenario. A good party is one where both of them are not present, because if both of them are present, they'll be glaring at each other. And because they're glaring at each other, everybody else is unhappy. Now, that is a question not on a single attribute's value, but the value of a pair of attributes. So Boolean, normal decision tree will miss it because it is making decisions based on whether Seinfeld should go to the party and whether Neumann should go to the party independently. But it really should make that decision together. And a way it could have done it and still be greedy is if not only it should consider one array attribute splitting, it should consider two array attribute splitting. If there are n attributes, there are n square binary attributes. Then you will be, even your greedy method would be optimal in that case. But of course, the greedy method is no longer fast. Instead of doing work which is proportional to n, now you're doing work which is proportional to n square. And after you did this, then I will come up with an example where the party would basically, whether or not the party is happy or not, depends on a clique of three people, whether they're all present or all absent. So now you will consider having to look for three array sizes. So it will become n cubed. Then I'll come up with an n power 4 and then n power 5. So eventually it's n power n or 2 power n. So the greedy approach to become optimal will have to be again n power n. I'm giving away the solution for the homework, because now I know that nobody pays attention anyway. Right? You look at the example homework and completely look at it from scratch. It's great, so this is completely independent of that. But it's an interesting point. Right? The greedy can be made optimal by by increasing the number of choices you are considering. The last time we did that, I don't know whether we may have talked about it in the case of hill climbing too. If the neighborhood over which you are considering the locally optimal move becomes bigger and bigger to include the entire space, then hill climbing is optimal. Okay? Anyway, so that's the problem here. Here's a little cute example, which is actually from one of the exams, actually. And it's trying to, I gave you some training samples of students who have been split, who have been characterized in terms of whether or not they're masochistic, anxious, and nerdy. And they're only true, false values. And whether they hate exam or not, they hate exams or not. Okay, so apparently false, true, false, yes, false, false, true, no, true, false, false, no, true, 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 yes. That's my example. That's my training data. Now you're trying to find a decision tree. Should we even find a decision tree? Yeah, because it's not done yet. Because half of the examples are yes, half of the examples are no. So the entropy is actually 1.0 right now. So you still need to split. The question is, should I split on masochistic, anxious, or nerdy? And you can quickly look at this. You can look at it more carefully after the class. But if you look at masochistic, there are two places where masochistic is false. One of which is hates exams, one doesn't hate exams. And two of which where it is true, one doesn't hate exams, one hates exams. Your intuition essentially tells you that splitting on masochistic is useless because you are no better off than before. And not surprisingly, if you throw it into this complicated formula, you will get entropy 1. That means the reduction of the entropy is 0. That means the remaining work is as much as before. Okay? And the same way, if you hit it on the nerdy, it turns out that despite your pet theory that nerdy people like exams, it turns out for this training data, that's not true. Apparently, even nerdy people, essentially, if you look at the entropy left, it's still 1. And again, if you look at the training, this is the number of training samples here is small enough that you can see why the answers are coming the way they're coming. But this algorithm, once you write it, can work also for thousands or millions of training examples, and you won't be there to look through them. In which case, why write an algorithm to begin with, if you are going to look into it, right? So then, when you go to anxious, not surprisingly, in fact, there are true anxious. There are 2 examples where they're anxious, and they're both yes. 2 examples where anxious is false, and the answer is no. So according to this pet theory, anxious people hate exams. That's it. It has nothing to do with nerdiness. It has nothing to do with masochism. And you will find that using your greedy decision tree learner. Okay? Now notice that this is not the only decision tree. There are many other decision trees which will capture this data correctly. This is the smallest decision tree. In this case, this is indeed the smallest decision tree. Optimal means smallest for us. And in the Seinfeld example I was telling you, there is an optimal decision tree which asks a paired question. Is Seinfeld and Neuman coming to the party? And the answer for that would be yes, 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 no, no, yes, no, no. Okay? And what you care about, and from those answers you can completely classify whether or not the party is going to be a happy party or not. It will only be an unhappy party when both of them show up. Otherwise, it will be fine in that training data. Okay? That is the smallest. But if you use the normal decision tree on that example, you will get a longer decision tree. You will ask more questions. And the assumption is the more questions you ask, the worse off you are. Because in some sense, one of the interesting things is you can always fit a particular Boolean function to pretty much any training data. Okay? Unless it is inconsistent. By the way, inconsistent can happen in the following sense. Suppose you went, you kept, if you kept pushing, okay, and let's say, so right now, here, you ask patterns, you ask hungry, and now this stuff still needs to be recursed down. Suppose there are no more questions left. Suppose you asked all the questions. By the time you came here, suppose this is a scenario where there's only patterns and hungry attributes. And so by the time you came here, as far as you are concerned, these examples are identical. And yet some of them are positive, some are negative. That means the data is noisy. Okay? When the data becomes noisy, in that case, what would you do? Decision tree learner can essentially say, instead of saying yes or no, it will buy a coin, which comes heads with probability 2 by 4, tails with probability 2 by 4, that means actually a fair coin, and tosses it. If it comes yes, heads, it will say yes. If it comes tails, it says no. That's the best way to deal with noise. You see what I'm saying? And how do you know whether you have noise? You ran out of all the questions to ask. And you, basically, when you run out of all questions to ask, then essentially all the examples here are identical as far as you are concerned. Because they're in the same exact branch. They have the same values for each of the attributes. And no more attributes are left. And yet some are positive, some are negative. That means the example, the data is noisy. Right? So at that time, you would then say, well, I would not, of course, there's nothing to split here anymore. So you would just say, with the probability, positives by total, it's heads, it's yes, and probability negatives by total, it's no. So here is my other question. We did this only here. We did this only here. What if I had come to a situation where after the first question, essentially I have correctly classified 99.99% of the examples, and a few are left. And if you don't feel like asking any more questions, should I ask? No, I can guess for the remaining ones. The same idea. The third question, can guessing ever be right? To answer that, to understand that, I will now give you a set of training data. Okay? The day of the week, color of my shirt, size of my shoes, length of my hair, length of the person's hair, rather, GPA of the person, and then the class. The class is, you tossed a coin, does it come heads or tails? Okay, this guy wearing a blue shirt and sort of hair does, and it came heads. So he corresponds to this row, heads. This is this guy, and then I correspond to this row, tails, and somebody else corresponds to this row, heads. I gave you some training data now. What's the right thing to learn here? And what would decision tree learning do? The right thing to learn, having realized where this example came from, the right thing to learn is to heck with all this junk. I have my own shiny coin. Right? So remember, the whole point of learning is not which decision tree you learned. Nobody cares about the decision tree you learned. They care about whether or not you are good at predicting the incoming data. Right? So then the test data basically, this guy is kept away for the test. And so we will now describe him. And you will say he just tossed the coin, predict whether it will come heads or tails. So you could learn a complicated pattern here and apply it to say, yeah, this will be heads or this will be tails. Or you can throw out this whole thing, toss your own coin, and if it comes heads, say heads. If it comes tails, say tails. Which one is the right thing to do? Right? You just have your own coin. Because all of these are completely irrelevant attributes. Will the decision tree algorithm realize it? No. Why? Because each of them, just by fluke, because of the training data, might have slightly different entropies. Okay? One might be 0.999965 left. One might be 0.99996401 left. And your greater than operator does not have a brain. It just boolean says, yes, it's greater, no, it's not greater. So you'll pick the one that has the lowest entropy left. They're all losers. They're all basically having 1.0 entropy left, essentially. But you are now splitting hairs. It's exactly splitting hairs to see who is winning. And you will learn a decision tree, which would look way more complicated than my decision tree, which says with probability half heads, probability half tails. Which is what I said you are allowed to do here when you have no more questions left to ask. Here I am doing it even though I have questions left to ask. Sometimes shutting up is the right question to ask, even though there are questions you can ask. Do you understand what I'm saying? And this is again the issue here. What is happening is most learning algorithms, including decision trees, overfit to the data. Overfit means you are splitting hairs. You are somehow trying to find a pattern in the data. And you will, if you are looking for a pattern, you will find a pattern. But the question is that pattern statistically significant? Okay? This is where actually the way decision tree algorithms handle this essentially is to check if this reduction, remember I was mostly looking at what is left and comparing them. But equivalently, you can talk about which is reducing the entropy the most. Is the entropy reduction statistically significant? If it is too small a reduction, it's not a significant reduction. So you basically say, I would refuse if the winner is winning by a hair's breadth compared to everybody else. And they are all essentially very, very close to being equal to 1.0 entropy left. That means they're all reducing the entropy only by 0.0000 something. One of them just happened to reduce it a little better in the 15th decimal place. Then what do? You would say, I declare all of you to be losers. And I will not ask any question. Instead, I'll just toss the coin up. That's how you handle overfitting in decision trees. Okay? There are two issues. One is overfitting is a bigger problem, and you are able to handle it here. Okay? So we ran out of time. Next time, I will actually also still want to do the decision boundaries. That means linearly separable examples using perceptron learning. And then we'll end the learning discussion and start going into first order.